Oh, yeah.
Before we start, there is one announcement, a program change. So Ravi Kannan, who was to have spoken on Friday, has agreed to move into the TBA slot today. So where it says 1615 to 1645 TBA, that will now be Ravi Kannan on whatever he was going to talk about on Friday. And then what will happen is Scopola will move from the final slot into that one that's been created. Okay, I think new sheets will be created, but the end result is you'll be able to get away half an hour earlier on Friday. So if you're catching something, that might be quite good for you. Okay, so I think that's the only announcement. Okay, so now I'm supposed to signal that we're recording, we're on air, and so next up, Yuval Perez, Microsoft will talk on whether extra updates can delay mixing.
Thank you. Good morning. So let me put title up and So this is joint work with Peter Winkler at Dartmouth. But it actually has its roots in the works of many people here, so I'll try to give a little indication of that. The title has a question mark because in general we don't know the answer. A typical instance where we don't know is connecting to Eric's talk. You're interested in coloring. You start from the worst configuration, the one that will take you the longest time to get within epsilon in total variation of the uniform coloring. And now, so you perform your sequence of updates, and then you add in a predetermined place, not looking at the coloring, you add an extra update somewhere. So in the step 100, you add an extra update that wasn't there before. So you get a new. So before we had maybe
place?
What?
At a predetermined.
At a predetermined place. So you had, and so you have the sequence of updates you had before, which you can think of as at random locations, or even think of conditioning on where those updates are. And now you're adding an extra update at the predetermined. Is that getting you closer in total variation to this stationary measure, or not? So we don't know, but the answer, we do know the answer for monotone systems. So the short answer is this cannot delay, no delay. So it does improve things, at least in the weak sense, for monotone systems. So the setup I want to talk about, things can be generalized, but don't want to be too general. So we start with a graph, and on the graph we have a spin system. So at every vertex there are a number of possible symbols or colors. The canonical case you can consider is the Ising model, where the probability, so the stationary probability pi of the configuration sigma is, except for the normalizing constant, maybe we'll have this form, I'll allow some constant, Jij, Juv, sigma u, sigma v. We can put a beta here, but the crucial thing is the beta and the j's are all non-negative. And this is an example of a monotone system. So the sigma here is in plus minus 1 to the vertex set of the graph G we have. So this is a monotone system. Monotonicity refers to an underlying partial order on the space. So here we have just the coordinate-wise order, and the fact, and it relates to the kind of updates that we're doing. So I'll write that down. So we will do Glauber or heat bath updates. So it means given configuration sigma, we choose a vertex V, typically at random, uniformly, but we'll also consider other ways to fix V, and then well, replace sigma of V using the conditional distribution so using the conditional distribution at V given sigma at all the neighbors of V, I'll just write sigma of W for W not equal to V. So there's a bit of abuse of notation here because I'm taking sigma. It had an initial setting at V. We erase that. So sigma of V, the original value is not necessarily flipped. It's just erased. And now it's replaced according to the conditional distribution given the neighbor. So we look at sigma on all the other vertices in the graph. In the distributions we're interested in have the Markov property, so it's the values at the neighbors that matter. Okay, and then the monotonicity means that if we start with two configurations, sigma and tau, and say sigma is greater or equal than tau in our partial order, so here it's coordinate-wise, then we can couple the update at V to get, say, the new thing, sigma tilde. Right, so we can update at any vertex V that we choose to update. We can perform the updates on sigma and on tau so that the new configurations, well, these are updates according to this Glauber or heat bath rule, and the new configuration is higher at when it started from sigma than from tau. So another way to say this is that if we have two configurations, again, sigma is above tau, then the conditional distribution at the vertex V given the rest in sigma stochastically dominates the configuration at tau. So we're going to use that relation between measures. So if we have two measures, alpha and beta, we write alpha stochastically dominates. This will be stochastic domination, right, which means two equivalent things that the two measures can be coupled so that a configuration chosen according to alpha is bigger than configuration chosen according to beta, but they live on the same probability space, or equivalently, that if you have any increasing function f and you average it with respect to alpha, this is bigger than when you average it according to beta, so for f increasing. So that's the definition of stochastic domination. So we're going to talk about monotone systems, and then the basic fact is that for monotone systems, an extra update only helps. So if here's a theorem. So in system, so you should really focus on the easing model, but it's more general. We will require that at every vertex, the possible spins, the possible values are totally ordered. So we have a total order at every vertex. Overall, that gives us a partial order, which is the coordinate-wise partial order, and we require this monotonicity condition. And then in the monotone system, suppose that we start at the top state. So in the easing model, this is the all plus. And we update vertices maybe at V versus V1, V2, so on up to Vk. And this gives some measure mu. Now, suppose I'll censor an update. So here is Vj, here is Vj, and here I'm removing the update at Vj. And this leads to a distribution nu. So again, we started at the highest state, which I can signify by this all plus. We do this sequence of updates to get either mu or nu, and then the theorem states that well, mu stochastically dominates nu, but what's important, more relevant, and doesn't follow from it is that mu, yeah, I'm getting it, okay. The other way, so mu, sorry, is mu has more updates, so mu is dominated by nu. So adding an extra update makes us more mixed. You know, I apologize. Let me be consistent with the locations of these. So we'll call this one nu, and this one mu, and we get, okay. Doesn't work, does it? Thank you. Have to change it like this. All right. Okay, so here there is an extra update at Vj. It's missing here, and that gives us a higher measure mu. Okay, so mu is higher than nu, and mu minus pi is further in total variation. Okay, so I want to comment that even though okay, mu is greater than nu, it's certainly going to be greater than pi. That's obvious. So I want to say that this relation by itself doesn't imply this. Okay, so just if you think of a simple example of, you know, here is a distribution where maybe mu is uniform on these 2 points, pi is uniform on these 2 points, and nu is uniform on these, then you see that mu dominates nu, and they both dominate pi stochastically, sitting above. Again, each measure is just uniform on 2 points. But mu is close, the distance in total variation from mu to pi in this picture is 1/2, while the distance of nu to pi is 1. So just the stochastic domination doesn't give us what we want. We need something more.
Question, is this
Yes.
result actually true for arbitrary partially ordered systems with arbitrary monotone updates? Or is it only in this case where you have a product structure and single site heat bath updates?
So the answer is somewhere in between those extremes.
Okay.
Yeah, so really figure out the right most level of generality. I don't know it in the most general case you described. I don't know a counterexample in that general setup. So really finding the right level of generality is another issue. But I want to quickly, so the proof of this is actually not hard. I want to quickly tell you why we got interested in this. The starting point is the utility of contraction arguments to prove mixing. So I think Eric briefly referred to this Dobrushin condition and gave an example with colorings where one gets fast mixing via contraction. This is also used in many other spin systems, in the easing model and so on, going back a long time. But one, but sometimes your system you feel is mixing fast, or you have other ways to know it's mixing fast, but the single site updates, as we have here, don't have the contraction property. The expected distance doesn't decrease. And then something that was, I think, first used in the uniqueness context by Dobrushin and Schlossman is to look at block updates and see that the block updates can decrease distance even when the single sites updates do not. So suppose you're working in a large, so the canonical example of this is suppose you're looking in a huge box and you have the Ising model on this box, and your temperature is above the critical but not far above, then if you do this dynamics and look at the expected distance between two configurations, in one step it might increase, and it does increase if you're close to the critical temperature. But if you instead consider a large but constant sub-box inside and do the update on that, so you typically will want to choose the location of this sub-box randomly here, then the expected distance after that update will go down. The expected distance between two configurations will go down, and that, for uniqueness purposes, a block update is just as good as a single site update. And so that's how that, I think, direction started. But then it's also extremely useful for mixing. And one route that has been followed a lot is to use block dynamics, use its contraction or its good properties, and then do some comparison argument to get a single site, so either going via spectral gap or log Sobolev inequalities. When you go via spectral gap, you lose something in this process. Okay. Now the next stop in this story is the work of Vandenberg and Brouwer from about 10 years ago. They were considering a different model, not a monotone one, monomer dimer, but they also had a setting where they knew that block dynamics mixes very fast, but single site does not. Or rather, they couldn't directly see that single site mix. So their argument gave them a contraction of block dynamics. It didn't work for single site. But in thinking of, well, how would we actually use this for sampling? Right? So again, I don't want to go into monodimer, so everything you can think of just Ising for this story. So if we want to do a block update, what does it mean? We take up such a box, we erase all the spins inside the box, and we replace them by a new sample chosen for the conditional distribution given everything outside the box. Okay? So that's very fast to say, but if you want to actually do it, you have to keep a big table telling you about these conditional distributions. It's not something that you really want to do. So then Vandenberg and Brouwer proposed, well, can we maybe simulate the block dynamics with a kind of single site? And the proposal is very nice, is to do a censored single site dynamics. So what's the idea? Take this box. I mean, it works in more general setting. Take this box and divide it into small sub-boxes by these lines. Okay, and now we're going to do single site dynamics, but they are censored whenever, so we choose a vertex at random and do an update there, except if it falls on one of these division lines, we skip that update. Okay, so we choose a vertex uniformly, but skip updates if they lie on the lines of division. Okay? And we run this for a long time. How long? Well, long enough so that the individual boxes here are going to be internally mixed. So since we think of these individual boxes constant size, this time will be of order constant n. So because it takes us order n steps, if n is the volume of the graph, to just sample anything in here. But the constant n will have a constant number of samples here, and the large enough constant is going to randomize this box and give us something close to the conditional distribution given its neighbors. So I should say that in Vandenberg-Brouwer, they did the argument a little differently, and they got an n log squared bound for this sensor dynamic. But in fact, if you look at their argument and just tweak it a little bit, you can see that you get an n log n. So again, the reason is that if you weight constant n, which is large enough, then here you'll be close enough to the block dynamics, and all you have to ensure is close enough so that the contraction condition still holds. So remember, we're assuming that we're in a situation, which often happens, that the block dynamics contracts the distance. If you weight this constant n number of steps, then you'll be close enough on this block to the block dynamics so that you'll contract the distance in constant n steps. So I'll write it down in Cn steps. We'll contract distance. So there's one caveat here. We'll contract distance between sigma and tau, provided that their differences don't lie on these division lines, because those differences we're not touching. But the thing is, after this number of steps, we're going to move the division lines, just say shift them by 1, and then repeat. And by just doing that, we we simulate the block dynamics close enough so that the constant n log n mixing that we know for the block dynamics with the worst constant works for the single site dynamics. So that was the Vandenberg-Brouwer idea. And then sometime later, in a conversation with Dana Randall, she suggested, well, maybe one can prove something about the actual original single site dynamics from this by showing that we can bring back the moves we censored without doing any damage. And that was what motivated our work, which was to try and see that. And in general, for instance, for the monomer dimer systems, we still don't know whether you can bring back the censored moves. So that's kind of a challenge. For monomer dimer dynamics on large box, do you have this n log n mixing that we know for the censored dynamics from the Vandenberg-Brouwer work? But for monotone systems, we know now that we can bring back the censored moves because of this theorem. So the conclusion is, whenever you have a block dynamics that has constant size blocks and that is contracting, then also the single site ordinary Glauber dynamics is contracting. But I have to be careful here. It's contracting when you, in one step it might not be contracting, but you have to run, if you run it for enough steps, it is contracting, and well enough to get the constant n log n bound. So
does this say, so this says that if the block dynamics is contracting with a mixing time n log n, then so is the single site?
Right. Well, if the block dynamics is contracting, well, if we're doing, if we're doing one block at a time, right? So what does contracting really mean? It means that we decrease the distance in one step by a factor 1 minus constant over n. Again, if you're thinking in continuous time, then contraction just means really decreasing by a constant factor less than 1. But if you're doing one block at a time, that's what we typically mean by contracting. And then that contraction automatically gives you the n log n mixing time. So that's the same as we all know, and was in Eric's talk, that 1 minus constant over n is the best contraction you can hope for when you're just updating a bounded set at a time. The best contraction factor you can hope for. So again, if you think of this two configurations that only differ at a single site, then the best you can do is if your update lands on that site, and then so the distance that you had started with 1, with probability 1 over n, it will disappear. So you get a contraction of factor 1 minus 1 over n. And what you want is that improvement will dominate whatever damage you could do by updating near a neighbor of the defect. Okay, so that's the background. Let me quickly sketch. Let me quickly sketch where does the proof of this come from? It's an easy consequence of a few lemmas, and I'll just state the lemmas to give the context. I won't go through, but the proofs of them are easy. So the key is to look at the right condition, which isn't stochastic domination. It's a stronger condition, which is monotone likelihood ratio, and see that that's preserved. So the first lemma is that the following. Suppose you have a measure mu, and mu over the stationary measure is increasing. Right? So this is a function. I just look at the density of mu with respect to the stationary measure, and look at that as a function on the state space, and assume that that's an increasing function on the state space. If sigma is less than tau, then this at sigma is less than this at tau. So if that happens, then also mu v over pi is increasing, where v, so again, this is for a monotone system. And by mu v, I mean what you get from the distribution mu when you update at the vertex v. Okay, so this is close to a statement that can be found in the Econis field 1990. They did it for total orders, but this works for this kind of orders, and it's not hard to prove. I don't have time for the details. So that's the first lemma. The second lemma, which is very easy, I'll just write it for reference, is that if you have two distributions, alpha and beta, and the ratio is increasing, and you have a totally ordered case, okay, then alpha stochastically dominates beta. So this is just one line from the definition and the fact that in a totally ordered case, if you have monotone functions, they're always positively correlated. That's all you need. The third lemma, which is just an application of the second, is that the ratio, okay, that, write it down. So if mu over pi is increasing, then mu stochastically dominates the update you get when you update at v. So the reason is that mu and mu v are very close. We have the distribution mu, and we have the distribution when we update at v. So we can think of these distributions by fibering them according to what are the labels of all the vertices except v. So suppose I fix all the labels outside v. Condition on all those labels, because they have the same distribution in mu as in mu v. The only change I'm doing is at v. So if I fix all the labels outside v, now I only look at the distribution at v, and then one distribution is just the conditional distribution of mu given the neighbors. The other distribution is the conditional distribution of pi given the neighbors. And these two distributions satisfy that the ratio, I mean, mu over pi is increasing. So we are in the setting of lemma 2 because we're only looking at the situation in v, and there the spins are totally ordered. So we can just apply lemma 2 to get lemma 3. And finally, lemma 4 is that if if mu is greater than nu, and you know something more about nu, and so that is nu over pi is increasing, then mu minus pi, then mu is further from pi. So that's exactly corresponds to that counterexample we had before, except so it shows that if you add the condition that nu over pi is monotone, then you just add this condition and you kill the kind of counterexample that we saw before. And all these lemmas are easy consequences of the definition. So the only game here is to somehow to choose the right definitions to look at. So let me just show you lemma 4. All the lemmas are, just take a couple of lines to prove. So why is lemma 4 true? Look at the set A, which is where, so the configuration sigma, where nu of sigma is bigger than pi of sigma. So when I measure the total variation distance between nu and pi, this is just equal. So this kind of set realizes the total variation distance. That's a standard thing you check when you define total variation, because A is just defined in terms of these measures. Now, okay, now use the assumption to see that this is less than mu a minus pi a, because, so here we're using, this is the key step, where we're using both assumptions. So the set where nu sigma is bigger than pi sigma is an increasing set. It is, so if sigma is in A and tau is bigger than sigma, that implies that tau is in A. That's what we call an up set or an increasing set. And that's true because nu over pi is increasing. Okay? So that's it, why A is an increasing set. And then the fact that mu stochastically dominates nu tells us that this inequality is going to hold, because that just means that we're taking the measure of an increasing set. So an increasing set, another way to say it, is that its indicator is an increasing function. So we're integrating that indicator with respect to mu that's bigger than with respect to mu. And then this is less than the total variation distance from u and pi, because that is just the soup of this expression over all possible sets. Okay, so the sequence of lemmas are just, a sequence of careful tautologies like these. And okay, and then once we have these 4 lemmas, then the theorem up there just follows. Because well, we just have to check that in this situation mu is bigger than nu, because and then this will follow from lemma 4. Again, we know that for both of these measures, mu over pi is monotone increasing, nu over pi is monotone increasing, so that holds. So we just go through to the case stage here. So at case stage, we get measures maybe mu k minus 1, which is equal to j minus 1, which is equal to nu j minus 1. And then, so that's the measure after j minus 1 steps. Then we do the update at vj, and we get a measure mu j, which equals here, because in mu we don't do that update. And this is going to be bigger. This is going to be stochastically dominate the measure nu j, where we do make this update. So this step is just lemma 3. Okay, so this step is just lemma 3. And then the monotonicity of the system means that all these additional updates are going to preserve this relation between the measures. So after we do, we get that that mu, which is the measure after case, after we do the k updates, is going to dominate nu. So it just follows from these lemmas and the fact that the definition of a monotone system tells us that if one measure lies above the other, then it's also true after we update at the same site. Okay, so that's the sketch of the proof of this, and it's just exercise to complete these lemmas. I do want to indicate one other type of application. Of these lemmas, besides to comparison of block and single site, and that's an application to systematic scan versus random update. So the usual Glauber dynamics, we choose a vertex at random and update there, then another vertex at random and update there. So we have, I'll use calligraphic R for the random dynamics, which is the usual Glauber. Then there is systematic scan, where we just fix a permutation of the vertices and go over them one by one and update there. And when we finish, we just start over according to, say, the same permutation. And finally, there's this special case of systematic scan that only works in bipartite graphs, and that's alternating. So if your graph is bipartite, it's natural and often done to first update all the odd sites, then all the even sites, and so on, because that's very easy to parallelize. Okay? And you can see that as a special case of systematic scan because you could do the odd sites one by one. It doesn't matter in which order, and then you go through the even sites one by one. It doesn't matter in which order. So how are these schemes related? So a general conjecture is that that in great generality, alternating is going to be the same as systematic, meaning up to constants, the mixing times for these schemes will be the same. Both of them, another conjecture is systematic.
That's just another way of saying that systematic scan, it doesn't matter what ordering you.
That's right. That's a special case of that statement. Thanks. And then another thing that systematic should always be faster. So the time for systematic, I use this for the mixing time under the scheme, should be always faster than random, again up to constant. But it shouldn't be much faster. So should be at least the time for random over some logarithmic factor. Okay, so we do know a log-n speedup can be achieved because if you have n sites and there are no edges between them, then systematic scan will, you just have to scan once through and you finish. So that's n steps. While the random updates, you don't need to visit every vertex, but you need to visit all but root n of the vertices. So you get constant, half n log n for the random in that case. So again, I'm ignoring constants. So these are conjectures that we don't know, but let me mention. So one corollary here is that the random is indeed at most, let's say, 2 log n times the alternating. And in easier one is that systematic is at most twice the alternating. So suppose we are in the bipartite case and the alternating makes sense. So why is that? And this is in this for monotone systems. And of course here you also need bipartite. So what is the reason, for instance, for the second? It's very simple. If you're doing the systematic scan, just censor all the moves in the odd sites. Then censor all the moves in the odd sites. Well, that's just the same as doing only the even sites, and your initial permutation doesn't matter there. So censoring all those moves will actually simulate the just doing the even sites, and then the next time you go through, censor the even just to do the odd sites. So you lose a factor of 2 because I'm censoring these moves, and then I bring them back and use this theorem to say bringing back updates can only speed up the mixing, it can't delay. So that's why. So we lose a factor of 2, but no worse. So that's for this second inequality. This first inequality is similar using coupon collector. If I do, I want to do the even sites, let's do random updates. Censor all the moves in the odd locations, and then look how long we need till we cover all the even locations. So let's, we need to sample them about, this is just coupon collecting, so we need to do them about n over 2 times log n over 2 times to sample all the even locations. So, so we do that, and then the next order n log n steps make sure to sample the odd locations. So because in the alternating, the order I do, the internal order between the even sites doesn't matter, I can just use coupon collecting for these bounds. So these are, of course, only special things that are far from these conjectures. In particular, right, it doesn't give you inequalities, good inequalities the other way, but it shows what you can do. And the last comment, another general conjecture for easing that I have is that if you have a bigger graph, it always mixes slower than a smaller graph, even if you rescale by the sizes. So think of continuous time dynamics where everything is moving at rate 1, then still a smaller graph should always be faster. And we don't know that in general, but this kind of method does prove it in special cases when the big graph is related to the small graph by just connecting something at one vertex. So this kind of picture, if you have this graph and you compare it just to the left graph, so the addition is only connected via a single edge, then that is indeed slower. We conjecture something much stronger happens. Let me stop here. Thank you.
So the small graph is a subgraph of the bigger one?
Yes.
You can't, this is related to Alan's question, you tantalized us at the beginning by saying, I'll do this for monotone systems, but we know it a little, or maybe you said somewhat more generally. Can you hint or even be explicit about how much more generally you know it?
Maybe offline, yeah. Because I haven't explored exactly to where the simple considerations generalize. Yes.
So you mentioned the examples where extra updates did delay. Do you have tiny examples?
Examples.
Well, say I have three sites.
So
Yuval, would you repeat the question?
yeah, the question was, are the examples where extra updates do delay? So first, they do delay if you can choose the location to update looking at the configuration. No, but in general, we believe that in general, starting from a worst case configuration, extra updates don't delay. We just, whenever we don't have the multiplicity, we don't have these tools to prove it. But a natural question is take the 3-state plots model and start from everything one color. You still have the monoticity, so there's no natural partial order, but still ask, does an extra update get you closer in total variation? And I believe the answer is yes, but just the tools are gone.
Uh-huh.
But there are these small counterexamples for something slightly different, for permutations.
Right. So once this succeeded, I got a little too optimistic and made conjectures about random transpositions. If you insert an extra transposition, that shouldn't make things worse. And Ander has counterexamples for that. So it's a different setting. It's not Glauber dynamics, but
there are also counterexamples for small easing models with
Well, it's not with the heat bath update. It's with the metropolis update, which flips with roughly twice the probability. But it's still monotone, right? And then there can be cases where systematic scan is non-ergodic. Whereas with random
not for easing.
For easing ferromagnet, you can, if I remember correctly, you can concoct situations where with a certain initial configuration, the systematic scan in a certain order will always flip the spins. And therefore, you don't visit all 2 to the n configurations, you only visit n different configurations. The systematic scan is not even ergodic, so its mixing time is infinity.
But that's the fault of Metropolis. So that can never happen in Glauber. So in Glauber, it's always ergodic.
Right, but then it partly answers my question, to what extent can you generalize from heat bath updates to arbitrary monotone updates? And the answer is not in general yes, because if you flip too much, you might get in the situation where you go into a cycle. So it's very important that the heat bath update kind of flips half as much as it can get away with.
Seems to be a natural pause at that point, so we'll finish the morning session.